Okay, we're going to get started. My name is Ken Boland. I know a lot of you, but not everybody. But it's my pleasure to introduce Professor Oscar Gonzalez. He's a professor in the Quantitative Psychology program in Psychology and Neuroscience at UNC. He completed his PhD in 2018 at Arizona State University. And then he came here and joined us. He's been an incredibly productive young scholar. Since that time in 2018, he's had over a dozen peer-reviewed publications, a couple of chapters in books. I mean, he's making us look bad.
Thank you.
No. Oscar does work in psychometrics. He also, which will not come out, he obviously does work in machine learning, which we'll be talking about, but he also does a lot of work in mediation analysis. So I know this is an issue of interest to some people here. In addition, he's done some substantive work on self-regulation. And today his talk will be an overview on learning and machine learning. So please join me in welcoming Oscar.
Pleasure to meet you all. I'm Oscar Gonzalez. Thank you, Ken, for inviting me. I really appreciate it. Also very nice to see familiar faces like my friends Zach Fisher and Patrick Curran from the program. So today what I want to talk about is pretty much give some basic information about what it would be like if you wanted to get into the area of machine learning. It's a hot and interesting topic right now. Again, I also do other things. But I ran into the area of machine learning out of need in terms to be able to tackle one of the problems in a grant that we were working on for the area of self-regulation. I believe that when somebody's going to give a talk, they should start with a promise, kind of like, hey, what are we actually going to try to get out of this? At least in this case, if you're not familiar with the area of machine learning, I'm hoping that by the end of the talk, at least you will know some of the terms and what they mean, and try to demystify a little bit about the area. So that's why this talk is going to be like intentionally broad and trying to cover a lot of little nuggets of things. If you're already familiar with the area of machine learning, at least here you will see a slightly different perspective in terms of how the things are typically presented. I'm going to try to talk more about how we would use this for the area of psychology. Within there, I'm going to try to talk a little bit of how I actually do or use machine learning for the two areas of research that Ken was talking about, like the area of statistical mediation and the area of psychometrics, kind of how Ken mentioned. I'd like to introduce myself in terms of where I've been and where I come from, because if you know a little bit about trivia, these three places have something in common, and that they all have quant programs. So I'm very happy to have been influenced by a lot of great scholars, at least for the area of quantitative psychology. These are my overarching motivations and interest in terms of why I do research. I'm interested into how we're able to go and assess some mechanisms for behavior change. How do we start healthy behavior, and how are we able to go on and maintain it if you're already doing that sort of behavior, especially because according to the NIH, smoking, substance abuse, overeating, and sedentary life cause 40% of deaths that are actually preventable in the United States. And if you want to start studying some of these mechanisms, there's multiple things that you kind of have to do to be able to assess them. One of them is to be able to measure the mechanism correctly, accurately. Also try to figure out if that mechanism actually predicts the outcome that you're interested in. And also we can intervene on that mechanism and in turn be able to change, stop some sort of behavior or try to promote it. So in the technical descriptors, what it used to be called when you were looking at databases, my areas are psychometric, statistical mediation, and machine learning. I typically like to motivate at least a talk in terms of how do we go and interact with data. Typically, our society produces a lot of data when you're interacting with a business, when you're interacting with the natural sciences or medicine. You're leaving a little piece of data behind. One of the ways I refer to it, and how other people refer to it, is some sort of data footprint or a digital footprint. Especially when we go and we swipe through life, we use credit cards and we swipe left and right on different apps. But it would be very interesting to go from this sort of raw type of data to something that is a little bit more useful here's an example of a data footprint, at least some things that I typically do every morning. You wake up, or I wake up, at least look at Facebook, I might interact with some ads or posts that I'm likely to interact with. I can check Gmail, be able to go on, and typically Gmail will tend to sort your emails into things that might be relevant to you, sort of promotions, personal, and things like that. Get ready to work, to go to work, listening to Spotify. Perhaps you might check the weather. At the end, you'll pick up some groceries in the supermarket, you use a loyalty card, and perhaps you might be able to have one of those fancy devices that you can talk to. It's just Alexa, turn off the lights. Particularly when you're thinking about this area, perhaps it became more relevant because now we're able to go on and do several things. When we're working with data sets, perhaps they can be described as the 4 V's of the big data boom, which is not that we have a lot of storage capacity, we have a lot of volume to be able to store this sort of data. We have a lot of computational power, we have a lot of different data sources, and then we're also trying to go and evaluate if the data is actually accurate. So that could be described as being able to work with volume, velocity, variety, and veracity. Perhaps another type of V that we have to think about whenever we're working with data is if it actually has any value to us. Machine learning has a lot of interesting applications. Typically for automated decision-making, image recognition, market forecasting, natural language processing, ad targeting, and fraud detection. And actually makes this world very exciting. But there's a problem. I don't do any of this. So I don't work in these areas. I know that you can use machine learning for this, or at least some of these paradigms. But this is not what I do. And you probably don't do any of these areas either. So my research is, or at least one of my areas of research, is to try to take some of these principles from machine learning and try to go and apply them to psychological research. Another of the ways how this can go about or be described is to, this is a term of statistical learning. Some of my research topics has to be able to go and use machine learning to determine how interventions work, and also to be able to use machine learning to develop assessments. And that's kind of how I go in and marry those 3 areas that I was talking about earlier. But probably since I got in here, one of the things that I've been trying to do by teaching courses for graduate students and undergraduate students, and also by talking to people about these areas to try to go in and lower the barrier of entry. If somebody wanted to go in and learn machine learning, what would be some of the things that they could go on and pick up in order for it to become a little bit more streamlined and they don't have to go on and struggle by trying to, go into a direction where they might not mean to go. So through that, I wanted to talk about some preliminary misconceptions about right before somebody's going to get into this area. What would be some of the things that are probably not going to get out of a machine learning algorithm? Because typically when I have tried to talk to people about this area, they usually mention like, hey, I wish I would have known this. I wish that before I spent 15 hours trying to go to this MOOC or reading about this book, I wish I would have known that I was not going to be able to do this. So that's why I like to, when I talk about this topic, I like to try to get those things out of the way before, actually trying to move on about something more specific. And if we wanted to be upfront, when you try to carry out a machine learning algorithm, or you're trying to go on and apply this in your research, some of the output that you might get from a machine learning algorithm is going to be a little bit different than what you're probably used to. If you're working with quintessential frequency statistics, perhaps you might be able to get some sort of confidence interval, some sort of p-value, in order for you to be able to make decisions. But with machine learning algorithms, that might actually go on and differ a little bit. And some of the methods that you might be able to go and employ, perhaps you might be able to get some sort of coefficient or some sort of graph that might be useful to interpret about what you actually went on to do when you carried out your analysis. Sometimes when you work with machine learning, you might be able to get some sort of summary information to figure out what were the most important predictors. For other machine learning algorithms, perhaps we might only care about the predictions rather than actually trying to break down what the model is trying to do. Perhaps the model became way too much complex, that interpreting a specific coefficient might not be particularly meaningful. But those are some of the things that we kind of have to get used to if we wanted to go in and move into this area. And man, there's a big gamut of algorithms that we could probably use. But we kind of have to go on and get a little bit comfortable before moving on, that whatever I'm going to be getting or the information that I'm going to be extracting might be different than the typical information that you're used to working with. So again, perhaps with some of these methods, at the end of the day, we might be more focused on the ultimate prediction rather than interpret the model itself. And when you're working with specific data sets, perhaps a machine learning algorithm might not be able to solve some of the quintessential problems that you're used to. We cannot really run away with some of the issues that inherently we have in data, such as being able to think about specific cause and explanation of behavior, to think about psychometric issues, such as measurement errors, bias, or even the interpretation of some of the predictors that we're going to have in there. There are personal biases that we have when we collect data are still going to matter, and that we might also have confounders that might be able to go and explain some of those relationships. So now that I was able to go on and just point out all the limitations beforehand, before now you're trying to think, so why do I need to do this? I think that machine learning is able to go on and provide several advantages or a different framework in how to be able to go on and think about data analysis. So again, I believe that this might be some of the ways how we can go on and think about the benefits of machine learning. I'm going to try to talk through each of these points as I go through the talk. But for example, one of them is that machine learning might be able to provide some sort of framework for data analysis when you actually think about learning a specific pattern. And I'm going to try to talk about what that actually means when we say that we're going to go on and learn something. Machine learning is also rooted in the generalization of results. That is one of the requisites if you're trying to go on and carry out machine learning. We ideally want to go on and develop models that are generalizable. Prediction in some of the models might actually be better suited for some of our research questions, especially when some of the relations between our variables are not particularly straightforward, and they might be a little bit more complex rather than just a simple linear relation. And perhaps significance testing is smooth in large data sets, especially because it's some of a lot of these statistics that we try to use, they depend on sample size. If my sample size is very big, perhaps working out with p-values might not be particularly meaningful. So at least for the rest of the talk, one of the things that I would encourage you to think about is about a research question that could be answered by prediction, and perhaps to try to take a leap of faith as I go forward with this. So at least for the general outline for the things that I'm going to be talking about for the rest of the talk will be to think a little bit about what data science actually means and how us as research scientists might be able to go on and be part of this big data science movement. Also, I wanted to talk about what learning means when you are in the area of machine learning, and also to try to introduce some of the terms that you might encounter. So especially whenever you hear about somebody trying to talk about these things, you're not completely unfamiliar. So again, the goals of the talk are to be able to go on and provide some sort of basic information in order for you to have some sort of framework of thinking whenever you encounter these sort of areas, and also to go on and demystify some of these concepts. But what I wanted to talk about is perhaps how us as research scientists might be able to go on and fit into this big data science framework. It is hypothesized that this kind of like became a buzz of data science because our society is becoming very data driven. We are actually going on and making a lot of decisions based on data. So perhaps if you think about a car, perhaps you don't really need to know how the car completely works, but you're able to go on and get in the car and be able to drive around. That it's actually a pretty big improvement. So being able to have people that are data savvy might be able to go on and actually help us in the long term. So here's a definition by the University of Michigan Data Science Initiative in regards to how they actually go on and try to define machine learning. If you want to come up, that would be very nice. I don't know where it is. Yeah, so for the Data Science Initiative, they went on and defined data science as the coupling of scientific discovery and practice in both the collection management, processing, analysis, visualization, and interpretation of vast amounts of heterogeneous data associated with a diverse array of scientific, translational, and interdisciplinary applications. And perhaps if you start thinking about this, right? Some of these aspects of what it takes to be a data scientist, this sounds very familiar in terms of what somebody that is trained to do research actually is expected to sort of know. Typically, when I introduce this area, I like to talk about John Tukey. And one of his papers is from 1962. The name of that paper was called The Future of Data Analysis. This was published in the Annals of Mathematical Statistics. Back in the day, in that journal, people tended to go on and publish things that were very theoretical, and they tried to go on and publish proofs. But then John Tukey sort of came around, and he was able to go on and write a paper and get into that sort of journal where he was trying to reflect about what the area of data analysis might be, that it's not just being able to think about the theoretical backgrounds of statistics, but actually think about some of the parts of the trade of what it actually means to do or to use statistics in order for us to interpret data. And he mentioned back in the 60s, and he had these visions that at least some of the major influences that were going to change in order for us to think more about data analysis were the following 4 points, where actually he ended up being right. One of them is that statistical theory was still going to matter, but also that the development of the computers were going to help us be able to go in and think a lot about how we were going to analyze data, that we were going to run into a lot of challenges by having massive amount of data, and that perhaps new disciplines were going to try to go on and think about the quantification of things, trying to move more into, for example, humanities. And now they're trying to go on and use statistical paradigms to be able to go on and interpret some of the things that they go on and do in that discipline. There was a conference around 50 years later where Donahoe, he is a statistician in Stanford, went on and reflected about how much that paper was able to go on and influence the field of data analysis. And one of the things that he mentioned is that if somebody wanted to go on and get trained in the area of data science, they needed to go on and be trained in a lot of different areas, such as data collection and preparation, data representation, computing, data modeling, data visualization, and the science about data science, essentially trying to think about the current practices. And essentially, perhaps at this point you're thinking, like, where in the hell are you going with this? Perhaps what I want to go on and convey by trying to put this in a bigger framework is that perhaps machine learning is a small and perhaps maybe the easiest part of data analysis, that we still have to worry about being able to take data to a workable shape and to be able to go and interpret some of the things that we have and some of the outcomes that we want to go on and target. But at least in this case, as research scientists, we might be very well equipped to be data scientists. Now that I was able to go on and bring it and ground it a little bit more into the things that we typically do, I wanted to talk a little bit about learning frameworks and what that actually means. So I'm going to be borrowing some of the language from Tom Mitchell and Pedro Domingos in order for me to be able to explain what learning is. Typically, before you go on and you think about learning, one of the ideas that you have to think about is, where does knowledge come from? And there are many different ways in how we might be able to obtain knowledge. Perhaps we might be able to have the things that we know encoded in our DNA, which were able to be and given to us through evolution. Perhaps some of the things that we go and experience on a day-to-day basis. And those are some of the things that might be encoded in our brain given experience. Perhaps another different way that you can learn is by reading books or talking to people. That would be a cultural way for you to be able to go and learn how to do something. But perhaps, at least recently, one of the other ways that we might be able to go on and get knowledge is by using computers. That perhaps by using some of these complex models, we might be able to extract information that we couldn't do with some of these 3 previous ways to be able to obtain knowledge. And one of the things that you might be able to notice is that perhaps as we progress from evolution, experience, culture, and computers, the way that we obtain knowledge becomes a little bit faster. When we think about learning, such as learning in the area of machine learning, it's important to go and introduce a learning framework. So here's a definition in terms of what we mean when something goes on and learns. Typically in this area, it becomes what we call a performance-based sort of definition of learning. That a thing, a computer, a model, whatever you want to call it, is set to learn from experience E with respect to some sort of task, and a performance measure if the performance in the task by measured by some sort of performance tend to improve with experience. Here is a way how you might be able to conceptualize it. So let's say that I want to go in and teach my dog a trick. So the task, for example, in this case would be I want to go on and get the dog to be able to fetch the ball. And in order for the dog to be able to do it, I need to go on and provide a specific experience. So for example, the experience might be play with the dog over the weekend with his favorite red ball. And then I kind of have to go and engage some sort of performance, and I can go on and mention that perhaps a way that I can measure performance is the reaction time from when the ball is able to go on and leave my hand to when the dog goes on and takes off after it. If you start thinking about learning in this specific aspect, then all of a sudden you start throwing a lot of assumptions around, a lot of things that you might perhaps require as you're trying to go in and teach, or you want something else to learn a specific behavior. So for example, the training experience matters. What if I only throw the ball twice to the dog? Perhaps at that point, the dog might not be able to go in and learn that specific concept. There's also some sort of focus on future behavior. Like, again, I would like the dog to play with me tomorrow, not just during the time that I was able to do it through the weekend. And perhaps I should also try to focus on the generalizability, that I just don't want the dog to be able to go after the red ball, but I also want it to go after anything that I throw it, perhaps a yellow ball or something that looks a little bit different. Those are some of the things that we sort of imply when we say that we're learning something. And perhaps you might try to take that sort of aspect and bring it on to data analysis. So what if I wanted to go on and learn a specific pattern? Perhaps in this case, I'm a psychologist. So let's say that I want to go on and estimate a respondent CESD score, that's a score on the depression measure, from some sort of patient or some sort of respondent characteristics. Perhaps the experience that I'm going to try to go on and provide a specific algorithm is a data set with scores and characteristics from other respondents. And then I need to go on and measure some sort of performance, and that will be the difference between what I observe from the respondent and what my model is able to go on and predict. But then from there, I still have to go on and think about the frameworks that I had talked about before. Perhaps I might be able to go on and care about the future behavior. I want to go on and predict in the future. The generalizability of my model. And perhaps how well that task or that experience is actually being provided. So for example, here the experience, I might have some sort of outcome and a bunch of predictors, such as the clinical history, current treatment, age, and sex. So let's say I try to go in and predict this. And perhaps through it, I can use a regression model. I can try to go on and impose a specific model where there is a linear combination between the predictors that I have and the outcome that I'm trying to assess. And perhaps the way that I try to go on and evaluate performance is by plugging specific values, at least for example, here for the predictors, multiplying times the weight that I'm able to go on and estimate. And that performance would be what I observe from that specific person versus what my model goes on to predict. And in this case, perhaps some of the things that we might try to go on and think about are if we're going to be overestimating, underestimating, or if my model is just correct. So again, if we think about this learning framework, some of the things that we have to go on and worry about are to be able to go on and define the task. That's some of the things that I was trying to talk about when I introduced the doggy example, which in this case will be to be able to estimate a predicted score on the CESD, to be able to go on and think about the experience that I'm going to go on and give my model, which is going to be a specific data set with predictors and outcome. And the performance in this case will be how close is my predicted value from whatever I'm able to go and observe from the respondent. And in this case, the learning boils down to be able to go and estimate these specific weights, to be able to go on and develop a model. And perhaps I brushed over a bunch of assumptions and things like that. So I'm trying to explain this. But the point of what I'm trying to go with this is that whenever you're thinking about some sort of these learning frameworks, you can apply them to the area of data analysis. And when you go on and you think about what does it mean when something learns something, you can go on and also apply it to the area of data analysis. We can easily take that specific part of the knowledge and apply it in this specific case. Perhaps at this point you might be thinking, is regression a machine learning model? Especially because we're not used to using regression in this specific way. Typically, at least traditionally, we've worried about trying to go on and fit models, trying to go on and interpret some of the coefficients and think a lot about standard errors, p-values, confidence intervals, and try to theorize where the predictors are related to the outcome. But if we wanted to go on and treat regression as a machine learning algorithm, we can try to go on and develop the models and the patterns in one specific data set. Then we might be able to go on and take the data set into a different environment and try to figure out how well our model was able to learn patterns that I was trying to go on and find. But we still have to focus on the generalization of some of these results because I'm trying to learn a specific pattern. In this case, for example, and I'm going to try to get into it a little bit later, but a perfect model in the learning phase might not be the model, but might be able to go on and predict well. I'm going to try to get into that point later. But again, this is just one model. This is just one way how I was able to go and estimate this specific relation. And perhaps I'm going to ask you to please let me abbreviate and use the following notation where I just go on and have some sort of function of a specific predictors in order for me to be able to go on and predict the outcome. And in this case, this is where machine learning models come. That we can use machine learning models for us to be able to identify and learn a specific pattern. And this is where these models goes on and they go on and fit in. And the thing is that there's many different flavors for us to be able to do that. And perhaps that becomes intimidating trying to learn them all. Because in this case, these functional predictors might be linearly related to the outcome or not. It might be estimated via non-parametric methods. Perhaps it might be very sparse. And only some of the predictors that I was trying to examine would matter. Or perhaps the model becomes very black box and very difficult to interpret. And the thing is that then you go on and you try to read research papers and people tell you like, we were doing machine learning. But what exactly were you trying to do? That's what at least I try to push in my classes, like, hey, try to be very clear in terms of how do you go on and learn the pattern. What is the task? What is the experience? What is the performance measure? Because if we don't actually try to go on and describe some of these things, how do we expect others to be able to go on and pick it up? I like to borrow Pedro Domingo's framework into how to go on and think about some of these machine learning paradigms. There are actually multiple ways to be able to go on and do machine learning. At least when I talk about these issues in my classes, I like to go on and tap a little bit at least into each of these areas. One of the ways to be able to do machine learning will be trying to go on and take a symbolist approach. A symbolist approach tries to go on and derive rules in order for us to be able to gain a little bit of knowledge. These are the people that use decision trees in order for them to be able to go on and say that, hey, you know, Hispanic assistant professor equals stressed out. The connectionists are the people that go on and do machine learning, trying to develop neural networks coming from the area of neuroscience. They believe that we can learn everything using a neural network, which essentially what that is. It's a big approximator of very different complex functions between the relation between predictors and outcomes. Trying to work with a neural network might be a little bit different than trying to work with something that is able to go on and derive specific rules. Another way to go on and do machine learning is to take an evolutionary approach, where the model tends to go and improve through time. Given some of the principles that we find in evolution, these are the people that go on and use the genetic algorithm. You also have the camp coming from statistics, where these are the people that use Bayes' theorem in order for them to be able to accumulate knowledge and be able to account for the uncertainty into some of the decisions that we might make. The last ones are the analogizers. Those tend to be the ones that are not that cohesive. These are the sort of thinking that we use in psychology and what I'm going to be using for the rest of the talk. The analogizers, the way that they learn is that they go in and they try to find similar cases. That, for example, if I wanted to go and diagnose someone, I can look at their symptoms. And if somebody new comes in and they have a similar pattern, I will classify them as being the same. Essentially, what they do is that they try to go in and take knowledge from one specific area, and they try to go in and transfer it somewhere else. This is very broad, and I actually take 6 or 7 lectures to march through each of them. I give it to you in 5 minutes. But essentially what this is that there are many different ways to do this. And it could be very intimidating trying to go in and just walk and try to learn each of them. What I'm going to do is that I'm going to try to talk a little bit about the way that we do analysis in psychology, and also try to talk about some of the models that the symbolists use, which also tend to be the ones that are a little bit more interpretable. With this, I'm going to try to take the analogies and try to go in and present to you some of the terms that you might hear when somebody's talking about machine learning. So perhaps now, if you listen to those terms, you at least will know what to think. I'd like to start with the definition of machine learning. Now that at least I've been trying to push these learning frameworks and all that, at least so you know what would be a working definition as you move through this. This from the SAS website. A machine learning approach or a machine learning method is a way to be able to do data analysis that automates the analytical model building. It is a branch of artificial intelligence based on the idea that systems can learn from data. And now you know what learning means. Identify patterns and make decisions with minimal human intervention. Here's a rough idea in terms of how machine learning works. Traditional analysis, when you're working with a computer, typically you will have some sort of input. Say that you have the number 2, then the number 3, and then you have some specific model and algorithm, let's say multiplication. Feed it to a computer, there goes the outcome. Typically we will get a 6. If your computer or calculator is working well. In a machine learning approach, we typically say that we learn from example. You will have some sort of inputs and you will have some sort of outputs. And I feed those to a computer. We say, hey, find the patterns, and out comes a model. The model, what it's able to do is to be able to go and map the inputs to the outputs. So essentially just turns traditional analysis around. We say that machine learning approaches learn by example because we give you a profile of people that meet specific characteristics and the ultimate output that you actually want to go on and be able to match to that. Typically, there's 2 rough types of machine learning methods. Typically, we will have the supervised methods, which is mainly what I've been talking a lot about. Typically, these are the methods that in the machine learning area we know the most about. Typically, you will have some sort of outcome and a set of predictors, and you try to find those specific patterns. We call that supervised methods. Unsupervised methods, what they're trying to do is that, hey, I just have a bunch of variables. Can you try to make sure that you find some sort of organization with them? And perhaps they might be better described as prediction method and descriptive methods. So whenever you see supervised and unsupervised, essentially what you're trying to do, or what I would like for you guys to think about, is that, hey, one is trying to predict a specific outcome. The other one is trying to describe what sort of data we have. I'm going to focus on the supervised methods, at least for the rest of the talk. Whenever you encounter this area, one of the terms that you might hear is the word lasso. Hey, I was doing the lasso. I was trying to lasso this. When somebody goes on and you hear about the lasso, I would like for you guys to think about variable selection. At least the lasso in this case will be an extension of linear regression. And this sort of method tends to be useful when you have a lot of variables and you want to make your models a little bit more interpretable. That perhaps I have 100 predictors, but only 5 or 6 of them were the ones that actually mattered. So by being able to go in and make the model a little bit more sparse, it might be more interpretable, and I can just focus on the predictors. They're actually important rather than for me to have to go in and carry 100 of these variables around, especially if you're in the area of prevention science and I can only intervene on you on a handful of things. perhaps I might want to know what's most important.
But we tried that before in social sciences. Isn't that the stepwise step down?
That is a different approach in how we can go on and do a specific variable selection. Both have different loss functions, but typically this becomes more popular. So this will be, at least what I'm trying to do here is trying to go and introduce some of the methods that you might be you might hear as somebody's trying to do this specific approach. I'll talk a little bit about how that specific methods might be a little bit different than the way that we're used to thinking about this specific process. Yeah.
So I guess as I understand it, by like selecting the predictors, like I come from a healthcare background. So like instead of just putting in every clinical variable we find, like, and we wanted to like come up with the methodology to predict if this person was likely to have cancer or not, you're saying in this case by lassoing, we would just restrict down to the variables that we've already previously identified are in fact risk factors for a particular type of disease.
Well, essentially what this is trying to do is, let's say that you go on and you feed a bunch of variables into your model.
Mm-hmm.
What it's going to try to do is that it's going to try to select the variables that are mostly related to the specific outcome, trying to go on and use a penalty that you have in there to be able to reduce the size of those specific coefficients. And given their size, those might be some of the coefficients that remain in the model or not. I can probably show you a little bit better if you in this specific slide. So for example, here, the way that we say that we're going to go in and lasso something is that we try to go in and make the coefficients a little bit smaller. One of the properties from the lasso, two of the properties, is that by doing this specific approach, one of the things that you might run into is that perhaps coefficients that had small effects might actually go on. So for example, those specific effects might not be effects that you might be able to find in other data sets. Essentially, it's trying to find something that is particularly more robust. So it's trying to go on and develop a model where some of the relations that you find in there might be more likely to generalize to other data sets. And the way that it does this is that it tries to go on and reduce the size of that coefficient. It happens that lasso has a specific property that it might be able to reduce the size of the coefficients exactly to 0. And if they are 0 in your regression equation, that predictor does not have influence on your outcome, and therefore you create a proxy to be able to go on and select specific variables in your model. Essentially, you're trying to go on and focus on sparsity. I can talk a little about some of the applications that I use, where I use the lasso for. We might not have time to cover everything I wanted to, but so here's an application. So, I mean, I'm a psychometrician, and one of the things that I focused on is to be able to go and develop specific measures. So, for example, here, what I was trying to do is, hey, can I actually go on and predict a depression diagnosis by a structural clinical interview, given some items that measure affect, because perhaps in specific instances, I might not be able to administer 16 items. Perhaps I can only administer a handful. So one of the things that I can do is that, hey, I'm going to try to go and predict this depression diagnosis using the items that I have in my measure. And by using the properties of the lasso, I might be able to go and select different items that are massively related to the outcome, that perhaps they don't particularly overlap. This could be one of the ways to be able to use it. Essentially, what this plot is trying to show you is each of the lines are a coefficient. Over here in the bottom is a particular penalty. That if I pay more attention to the way that we do lasso, perhaps some of the coefficients might be able to go and estimate it to be exactly 0. We could also try to use a sort of stepwise sort of approach to be able to do this. But here's another way that you can go on and do it. That would be an application of the lasso, at least here, for example, would be to be able to select items from, to be able to make up a questionnaire. Yeah.
How the optimal penalty is chosen?
So I was not gonna talk about that, but the way that you would do that is by a specific approach called k-fold cross-validation. So essentially the way that you would do it is that you would figure out the relationship between the penalty and the prediction in a specific data set. So that tends to be the motivation of K-4 cross-validation, which is, hey, what is the relationship between paying this much attention to the penalty that I have in my lasso to how well I'm able to predict in another data set. Because I don't have time to go through this, but this will be the items that tend to be selected out of those 16. Another of the approaches that you might go on and encounter if you're working on the area of machine learning is a decision tree. And whenever you hear about that, I would like you guys to think about a decision-specific process. Essentially, what a decision tree is trying to yield for you is a specific collection of rules that will help you determine a specific classification. Essentially, you have some sort of approach. The output will kind of look like this. And essentially, what you're trying to go on and have is that at the end of the day, you have a model that tends to be simple and interpretable. The whole point of the tree is trying to find clusters of cases where people tend to be more similar in the outcome. One of the applications of how I use trees is to be able to go and administer a test adaptively. There might be situations where I cannot administer all of the items. Perhaps I just need a handful of them. The previous example for last is to be able to go and determine a specific diagnosis. In this case is, well, what if I just want to administer the items adaptively in a way that I can get a predicted overall score? So I can go on and get the sum score of a person and predict it by the individual items. If I use a decision tree sort of method, perhaps I might get something that kind of looks like this, where it's going to give me some sort of routing in terms of what item I should administer next. In this case, I mean, for this silly example, let's say that I administer item number 4. If you get higher than a 4, I will then administer item 16. And if you have greater than a 5 on item 16, I will administer item 2. And instead of me using 20 items, I can try to get a predicted score, roughly with around 3 or 4. But this will be an application of a decision tree. Another of the terms that you might go and encounter will be a random forest. And when you think about a random forest, one of the things that I would like you guys to consider is that essentially what you're doing is that you're predicting for many trees. Because decision trees, what I showed before, they tend to have a limitation, is that they tend to be very unstable. That if I go on and actually change my data set slightly, perhaps my optimal tree would be a little bit different. So perhaps one of the things that you should go on and think about is that perhaps I might be able to predict from multiple trees, not just from one. So essentially what that is doing is that it's going to go on and take the concepts of decision trees, now make a lot of them, and essentially work on like committee voting or wisdom of the crowd. Essentially what you will have here is you will have the data. You will take bootstrap samples from this. Essentially, you're going to resample your data set with replacement. In each of these bootstrap samples, you will grow a tree, get a prediction, and then average it. With some other idiosyncrasies in between. But essentially, that's what you're doing. You're trying to take the concept of the decision tree and make it a little bit larger. I think I might need to go a little bit faster here. But essentially, the way that I have used decision tree or random forest is that instead of me trying to go on and estimate mediated effects to try to figure out how an intervention works, the way that I have used it is that I might not need to assume that I have a linear relation between a specific mediator or mechanism of behavior change and the outcome. Perhaps the relation might be a little bit more complex. And if it's nonlinear, I could try to approximate it with a model that will be similar to a random forest. One of the things that you might think about as you're going and encountering this area of machine learning is that you might just figure out, like, hey, how do I pick an algorithm? You just go on, pick one, and move around. When people talk about the best algorithm, I guess this is, I'm starting to close down the talk. It becomes very difficult to know a priori what algorithm is going to work well in any given instance. There's this thing that is called the no free lunch theorem. That essentially what it's trying to say is, well, we do not know in any specific instance if my data is going to meet all the assumptions and is going to be optimal for a specific algorithm. perhaps one of the ways to try to go on and overcome this sort of concept is to try to use them all. Use algorithms that you have handy, and then we will do a process that is called super learning, which what that is going to try to do is that it's going to try to combine different aspects of the algorithms to give you one joint solution. That I'm not going to just choose one of the algorithms, I'm going to use multiple. And I'm going to use a procedure to be able to try to go in and combine them. This becomes a little bit more complex. Typically, when I talk about these things, people will be like, yeah, but which one's the best, like for real? and if somebody puts a gun to my head, if I was stuck in an island and I only had to choose one of the models, I would rather stay with a random forest, which is the one that I was trying to talk about before. It might not be the best model in all situations, kind of how I mentioned, no free lunch theorem. But a random forest approach tends to be like a good off-the-shelf sort of method, where it's able to go on and handle continuous categorical variables without very minimal transformations, and also gives me a particular mechanic that is able to help me interpret, which are going to be some of the models that tend to go on, or some of the variables that tend to be a little bit more informative in any specific instance. This might be the last concept that I was going to talk about, which is probably the most important, which is cross-validation. When you're thinking about the area of machine learning and you're running to the concept of cross-validation, I would like for you guys to think about model generalization. That when we're thinking about the area of machine learning, one of the things to consider is that the way that it differs from the traditional exploratory analysis, stepwise, forward, backward selection and things like that, is that it brings a framework where we go on and develop our model in one part of the data set, and then we take the model and evaluate in a different part of the data set. We try to go on and separate those two steps, and that tends to be a requirement for the area of machine learning. We know in research that we're supposed to do that very clearly, except that I don't read a lot about that in papers. Essentially, what cross-validation is trying to promote or is trying to do for you is that the model tends to be evaluated in cases that it has never seen. In this particular concept, we develop a model, we learn some patterns, we take them into a different environment. In a different environment, we still have the outcome. We just pretend that we don't have it. And then what we do is we try to go and estimate how close is what we found or what we predicted compared to what we have observed. You might think that this is very similar to replication. Essentially, kind of follows similar dynamics. It's try to go on and figure out how generalizable are some of these methods. But essentially, what we do here is that in replication, we tend to go and carry out another study and re-estimate the model again. And what we focus on are if we have a specific general directionality or general patterns that we have found before. In cross-validation, what we do is that the model is estimated once. We grab the model, where I tell my students, we freeze it in time. We take it into a different environment, and we see how well the model that I have developed predicts in a different data set. I don't re-estimate the model again. The model has already been estimated. By doing this, perhaps we might be able to figure out how generalizable is what I have already found. And this is where it branches out from traditional exploratory analysis, where typically in exploratory analysis, we try to go on, find specific patterns, and then we try to go and interpret what we have already found. In this case, if we're going to do exploration, we're able to do that. Cross-validation allows you for the flexibility in model development. But if you actually want to write about this, you need to make sure that you take your model to a different data set to see how well it performs. And it's just to start closing the talk. Arguably, this is the most important thing that machine learning is able to go on and provide for. The generalization of the model that we're going to go on and develop to be able to go on and take it into a different environment. We know that we're supposed to do that. as psychologists, as research scientists, and whatever, we rarely do. Pretty sure, yeah. So ideally, this is what this field provides for you, because these are ingrained into the culture of working with a specific area. There's a couple more of the things that I wanted to talk about. Algorithmic bias. When you hear about algorithmic bias, think about that machine learning went wrong. There might be situations where we might be able to do or use machine learning for automatic decision making. It happens that this is more relevant than what we have taught. This is an article in Nature from last year that essentially for healthcare referrals, it was discriminating against people from certain ethnicities. So we kind of have to be careful and transparent whenever we're working with these specific models. But essentially, that's what I'm trying to push, that whenever we try to go on and think about this specific area, for us to be very clear about the steps that we're taking, that we try to understand what's going on behind, even though the model might not be completely interpretable. But essentially, whenever we're thinking about machine learning, the way that we go and we carry through this is that we try to learn patterns in one data set, and then we take whatever we find and try to figure out if it holds in a different data set. We evaluate what we found. We focus on generalization, which is essentially what this field is trying to go on and push for you. But we're not going to run away from our typical problems. That all of it is going to depend on the way that we collect data and we interpret predictors, and to actually try to go on and make something that is particularly meaningful. I like to plug in that I'm teaching class in these areas. This is the one for undergrads. So now psychology undergraduates are trying to go and learn a little bit about that. Very surprised that they actually can do it. Bad thing is that they don't really know inference, statistical inference. The good thing is that they don't really know statistical inference. So it's kind of like, hey, oh yeah, I'm going to cross-validate my model, because that's what you need to do, right? So that's now taken Nature for them. I'm currently teaching a class for graduate students, 791, but that number might actually change. It goes in depth into a lot of the stuff that I actually talked about, tried to talk about some of these concepts and things like that. Actually, at the end, they have to focus on ethics. So let's see how they do this semester. I think you guys might have access to the slides, but these are some of the resources in terms of where you can learn more. These are the books that I use for the class. I guess they're all from Springer, from the Springer series. I don't work for Springer, but they probably should pay me. Here are some ways that you can go on and learn a little bit about the software. I use R almost exclusively, and Carrot is a great package if you want to go on and do cross-validation for your results. But probably the last thing that I wanted to go on and say is that whenever you're working with this area, try to be honest. Try to be transparent about the things that you're doing, because these methods are highly exploratory. But the concept of cross-validation will help us. Being able to go on and explore as much as we want, but whenever we go on and we find and we determine a model, we try to make sure that it performs well. Hopefully, for me, trying to go and introduce some of these terms, like learning frameworks, cross-validation, and things like that, might help you lower the barrier of entry. And if you want to go on and pick up these methods, at least you have a little bit of an intuition in terms of what they're trying to do. When you're thinking about what does it mean to like learn something, and perhaps lastly, whenever you're trying to go on and carry out a specific project, make sure that you specify clearly what is the task, the experience, and the performance metric before you go on and you tell me what you found. Thank you. I wanted to leave a couple of minutes for questions, and I'm happy to also stick around for a little bit. Yeah.
So one of your examples was using machine learning to kind of narrow down which questions from a longer battery you might ask.
Right.
But it seems like there's a really strong foundation in psychology of having all the questions in order to get your paper into a place where psychologists are going to review it. So how do you trade off? I mean, there's a huge advantage to having to only ask 5 questions instead of 20, and yet has the field progressed to accept that kind of change?
I mean, so I live in both worlds. I'm a psychometrician by training.
Right.
So I went to work with a guy that was, the ultimate hero on measurement invariance and measurement bias. There is a lot of, so now you have a lot of things into play.
Yeah.
Typically, you come from a psychometric background, which is what I did for my comms and dissertation. And when I interviewed here, that's what I talked about. Typically, one of the things when you're building a questionnaire, things that you should worry about is to be able to think about the concept validity, to be able to go on and find a way you can interpret all this stuff. Now, there is a pretty big market on trying to go on and have an educated approach to be able to select items that are that essentially will give you optimal properties, also in the area of psychology, also in the area of psychometrics, because we realize that we can measure everything by giving all of them. There's ways to do that in psychometrics that we're pretty good at doing, which is being able to fit an error response model and figure out where it would be the optimal or where that specific item is going to be discriminating people. When I mean discriminating means like trying to go and measure them at a specific range. This is one way to do it, and a lot of my work has been on trying to compare if we lose anything by moving into this specific framework. But I think that as long as we're able to reduce the number of items, try to show that we can cover the content span that is still interpretable in terms of what we had done before, I think that it's, I think that the paper will still be publishable. That's the ultimate question. Because essentially the way that I got into this business was that specific problem. We were trying to measure self-regulation in one of the grants, and self-regulation is very hard to define. Mindfulness, ventureness, self-control, grit. So the way that they went on to do it is like, well, we're just going to administer 600 items.
Right.
So I'm a psychometrician. I'm like, I know how to do that. That's a verb selection. That's a psychometric problem. But people were fighting me like, well, this could be a variable selection problem, machine learning. So I was pushed to be able to go on and get into this field, and some of my work is trying to think about the trade-offs. It's just using one or the other. But I think that at least ultimately, if we're able to go on and demonstrate that a more cohesive and concise number of items are able to hold similar properties than the longer one, and if we can show that there is a specific way to save time, effort, money, burden, it would still be useful. Very happy to talk more about that. That's exactly what I do for a living. Yeah.
Aren't you still left with the problem of knowing whether the outcome is what you think it is? Because you could have a beautifully performing instrument, but it's not capturing.
Mm-hmm.
So if you've got a hard outcome like mortality, that's easily measured. But and what if?
No, exactly. We're still banking that we are able to go and interpret both the predictor and the outcome, and that is specifically relevant. Kind of how I mentioned before, like we're not going to run away from those specific problems of trying to go in and either select items or use a specific predictor to be able to optimally predict what we think we're trying to predict. One of the things to think about is that these methods were developed in the area of banking, in the area of cybersecurity, where we're actually able to go on and think about very specific outcomes. But some of the things that I deal with on a day-to-day basis, we run into that validity sort of question. So again, at least in this case, it's trying to go in and take some of those principles and see they could help us, at least a little bit, to be able to answer that specific question. Yeah.
Does this relate to the big issue in the social sciences of inductive versus deductive reasoning? You're proposing a kind of inductive approach. Economists and sociologists have had the battles. Economists criticize sociologists for not being deductive enough and having enough theory, and for playing with the data more.
Mm-hmm.
And what you're proposing is that we actually look at the data, and maybe from the data we can learn some things about predictors, and ultimately get back to revising and developing a new deductive or theoretical model.
That's a, where is it? Right here. It's an assemblist. Those are the people that try to do inverse deduction. So the way that we try to go on and learn something is by trying to go on and figure out specific patterns go backwards. So that is one of the ways to be able to go on and do machine learning, and one of the ways that it's have been proposed that in order for us to be able to like learn something, we try to look at specific rules, try to come up with some sort of knowledge, and then work backwards. It is one of the camps, and that is the one that pays the most attention. Like that is the camp that pays the most attention to that. I mean, I live in both worlds. I would say that, I mean, theory still matters. A lot of the ways that I use these specific applications, maybe I'm not using purely machine learning, because a lot of the times when I'm working with some of these approaches, some of the predictors have already been curated. Some of the things that I fit into it, those are things that I believe are going to be associated with the outcome, and perhaps that's not going to be shown perhaps in mine. So I already went on and biased, not specifically biased in, not in the way that it's right, but in the way that I already pre-imposed what I thought that was going to happen. But yeah, that is one of the ways to be able to go on and think about this, trying to find specific patterns, work backwards, especially if you're thinking trees and things like that. That's a very interesting question. Thank you.
I think we'll have to end here, but if there's individuals who have additional questions, please feel free to see Oscar. But
Yeah.
Thank you again.
Thank you all. I'll be here and